benzene reacts with fuming sulfuric acid. Fuming sulfuric acid has sulfur trioxide mixed in. So sulfur trioxide is the actual electrophile, and we worked about it, right? We talked about it, all of that stuff. Isn't that right? Yeah. Okay. I'm just trying to remember where we were on Monday. And then we wrote the mechanism for this. That's where we stopped. Yes? Okay, cool. So one thing very useful about this reaction, as we'll discuss as we go forward, we'll discuss multi-step syntheses and all, and we'll talk about this. But something that's very useful about this reaction is actually that it is reversible. It can go back to benzene simply by using a dilute acid. We don't need to know the mechanism of the reverse part of it. We just need to remember that actually sulfonic acid can be hydrolyzed back to benzene by simply taking dilute sulfuric acid instead of fuming sulfuric acid. If you just use dilute sulfuric acid, it goes right back to benzene. So just please make a note of that. Okay, let's look into the next reaction for us to write a mechanism of is nitration. Did we write this one as well?
No.
Okay. Nitration. So benzenes can be nitrated, meaning that benzene can be converted into nitrobenzene by using, give me a second. Did we discuss the structure of the NO2 group? Do we know what is NO2? What does NO2 look like? Did we talk about what is NO2?
We did.
N double O
So
and
keep that
single
in
O.
mind, guys, because again, those are the important things. NO2, but what is NO2? Well, NO2 is where, again, Lewis-Dot structure, where there's a negative formal charge, positive formal charge, because that affects a lot of its characteristics. So we should always know structure. Anyways, so this reaction can be done by taking a mixture of two acids, and those two acids are nitric acid and sulfuric acid. The mixture of the two allows us to do nitration reaction. Okay? Let's write a mechanism for this. Does anybody have access to their pKa tables?
Yes.
Please, can someone fish it out? I forgot my pKa table. Can someone tell me what is the pKa of nitric acid and what is the pKa of sulfuric acid?
Nitric acid is
Say that again.
nitric acid is negative 1.3.
Negative 1.3, and how about sulfuric?
Negative 3.0. Yeah.
Negative 3.0? Something around that. Is that what you guys have? Okay, so nitric acid, sulfuric acid, they are both acids, but which one is the stronger acid? Anybody? Which one is the stronger acid? Negative 1.3 versus negative 3.0. Which one is the stronger acid?
Whichever one is negative 3.0, H2SO4.
Exactly. Lower pKa, higher acid strength. Higher pKa, lower acid strength. The negative sign kind of throws us off, right? Exactly, I know. It's the number line, basically. 0 and positives and negatives. But yes, you're absolutely right. This is the stronger of the two acids. So if I have the two together, if I have these two together, who's going to act as the acid and who's going to act as the acid? Who's going to donate a proton?
Sulfuric acid.
Right? Then who's going to take the proton? Exactly. If I have only these two together, that's a stronger acid. It will donate a proton, so that will have to take the proton. That's a very weird concept to think about. Nitric acid, one of the strongest acids in this entire acid-base spectrum, and yet it's acting as a base here. Why? Because it's not about me, it's about the other one, and therefore I decide to do this. It's always like that. Does everybody understand? Yes? Can you please draw for me the Lewis dot structure for nitric and the Lewis dot structure for sulfuric in 20 seconds?
I have a quick question.
Yes,
Is
please.
there water in the system?
Yes,
So
but
why
we are
would-
taking concentrated.
Okay.
So, yes, there's hydronium ion concentration there too, but we will also have high amounts of these as well. Absolutely, there's hydronium, no doubt about it. So, can someone please tell me what is the Lewis dot structure for nitric acid and the Lewis dot structure for sulfuric acid?
Nitric acid.
Anybody?
N double O.
Okay, N double O,
With 2 electron groups
okay,
on the O.
2 lone pairs,
Two lone pairs on the
okay,
And then single bond O
single bond O,
with 3 lone pairs
okay.
and a negative.
Yeah, because 3, so that's, what else though?
Oh, and then.
You're right, that's gonna be negative, okay, what else?
And then another single bond O
Uh-huh,
with 2 lone pairs,
and,
a bond to hydrogen.
right? So then should nitrogen also have a formal charge?
Yes.
Which would be what?
Positive.
Do you agree?
Mm-hmm.
What about sulfuric acid? Lewis dot structure for sulfuric acid.
S with 2 double bond O
Mhm.
groups and 2 single bond OH groups.
Mm-hmm.
Okay. There are no formal charges here, they're all zeros. Okay, cool. So, sulfuric acid is the stronger acid, that means it donates the proton, so nitric acid decides to act as a base and take the proton from the sulfuric acid. What does that create? What does that make? So, nothing else is changing, except this has an extra proton. I'm not drawing the lone pairs. They're there, of course. And of course, HSO4 minus. Agreed? Yes? What
Yep.
am I missing?
The signal, the plus in
Where, what?
H2, H3, I mean, whatever.
Agreed?
Yes.
Okay.
Also minus.
So what does this have? Which you've seen many times before. A good leaving group.
A good leaving group.
Absolutely. So once the nitric acid gets protonated by the stronger acid, sulfuric acid kicks out water because it's a good leaving group. Everybody okay? Of course, I didn't write the formal charges, but you can go ahead and write those if you'd like to. It's totally up to you. Sorry, I'm thinking about something. If I'm going to write the formal charges, then I'm going to push my arrows differently, because then otherwise it will leave nitrogen looking very weird. Yeah, so if I'm going to show formal charges, I'm going to push water out. What does that make? That makes this ion. This ion is called nitronium ion. This ion is called nitronium ion. And that is the electrophile. In nitration reactions, the nitronium ion is created first by nitric acid taking a proton from sulfuric acid, then kicking out water, creating the nitronium ion. Once the nitronium ion has been formed, that is when benzene comes in and attacks the electrophile. When it attacks the electrophile, it creates what we call a sigma complex. Does that ring a bell, everybody?
Yep.
Yes.
Yesterday.
Sigma complex.
On Monday.
Sorry, I missed my charges. And what does the sigma complex need to do in order to become the product?
Give away a proton.
Give away a proton. So again, who's taking the proton? And there's so many options here. It can be bisulfate, it could be water if there's a little water around. Well, there is water around because we did kick out water as well. So something is going to come in and take a proton and recreate aromaticity and give us nitrobenzene. That's nitration. Everybody okay with nitration? Okay. Please remember, all of these mechanisms are really the same, except the difference from one reaction to the other is how or what is the electrophile. Once the electrophile is clear, then everything is the same. So go ahead, why don't you guys practice this mechanism one more time by taking 1, 2, what is it? 1, 2, 3, 4, 5 tetramethyl TE benzene reacting with nitric acid and sulfuric acid. Please go ahead. Tell me first what will it create. Let's do that first, and then we'll write the mechanism. What would that create? Anybody? What's the structure of 1, 2, 4, 5 tetramethylbenzene? Benzene ring with?
Methyl group on 1, 2, 4, and 5.
Isn't that right? So you're reacting this with nitric acid and sulfuric acid. What kind of reaction is it? Is it halogenation, sulfonation, or nitration?
Nitration.
So where is the nitro group going to go?
In one of them.
One of those. Does it matter where? No, it's
No.
symmetrical. So what's the product? The
Um,
product is 1, 2,
4,
4, 5
5
tetramethyl 3-nitrobenzene. Isn't that right?
Mm-hmm.
If you had to name this compound, isn't that what you will call it? 1, 2, 4, 5 tetramethyl 3-nitrobenzene. Let's write a mechanism. Please go ahead. You do it. And when you're writing the mechanism, you got to start from the top. You got to show how or what the electrophile is, because that's important. And then the benzene comes in and attacks the electrophile. So please go ahead. You do it. I will also do it. We'll compare. The whole thing. Yes, exactly. Starting from the top. Yes, exactly. So if you get a question like this on the exam or quiz, yes, we are starting from the beginning. So
start with the
and then that kicks out water, creates nitrogen. That's the first step. Electrophile has to be created. Once the electrophile is created, now benzene can come in. And attack the electrophile. Oh, shoot, we are doing tetramethyl. Sorry. Yeah, sorry. There we go. Okay, so then that can't go there. So, there. Get the sigma complex. Once you get the sigma complex, then some things such as water, because obviously we are creating water, plus I'm sure there is water in the system, is going to take a proton and recreate aromaticity. Everybody okay? Make sense? Yeah?
Yep.
Now, a side note to make, nitration converts benzene into nitrobenzene. Nitrobenzene, this is also synthetically a very important reaction. The nitration reaction is a very important reaction because the nitro group can be reduced to amino group. This is a very important process for us to be able to get aniline. How else do you get aniline? Well, you first nitrate the benzene, put a nitro group on it, and then reduce the nitro to become amino group. And the reagents needed to reduce the nitro into amino is, we will either take tin or iron. Choose one of those two in an acidic environment. And then, of course, we have to basify it, so neutralize the acid, we have to use that. So that step, again, mechanism for that step is not necessary, but nitro can be reduced to amino by doing this two-step process. So that's why that reaction is actually very useful.
Do we know that mechanism?
No, we don't need to know this mechanism. Everybody okay? Yes? Next reaction we'll talk about and write mechanism in details for is the Friedel-Crafts alkylation reaction, where benzene is being converted into alkyl benzene, putting an alkyl group on the benzene. So let's get into that reaction details. And the last one, of course, after that is Friedel-Crafts acylation reaction. So we start with alkylation. This is the reaction where benzene can be converted into alkyl benzene. The reagents needed for this are alkyl halide with a Lewis acid catalyst. Just like halogenation, do you guys remember? We have to use a Lewis acid. Similarly, we need a Lewis acid catalyst. What is X? What are the X's what X's? Can't talk.
Chloride and bromine.
Thank you, you got my point. So, what can Rx be? Rx can either be RCl or RBr. If it's RCl, what would be the Lewis acid catalyst to be used with it?
ALC.
Exactly.
ALCl3.
Same as halogenation. If it's R bromide, then what is the Lewis acid catalyst we will use with it?
Iron-free
Fe
bromide.
Exactly.
bromine.
Same as halogenation. In fact, the mechanism is also very, very similar to that of halogenation, as you will see. Very similar, with again a little bit of difference because we have alkyl group in there, except so, but you'll see the similarities. Okay, so why don't we take an example and then write the mechanism? Is that okay with everybody? Or, yeah, let's write them. Yeah, please.
Wait, are those steps together or is it?
No, no,
just-
no.
Okay.
Oh, no, no. Depending on what the Rx is.
If
Is
it's-
that, are you talking about this?
Oh, I see what you're saying.
Right,
Okay.
so, or,
Oh,
depending if Rx is RCl, then you use that as the Lewis acid catalyst. If Rx is this, then you use that as, that's what I.
Yep.
Yeah, absolutely. Okay, so let's use an example and we'll write a mechanism and do a few more examples. This one we need to spend some time on. So let's say, for example, we are reacting benzene with, what should be the Lewis acid catalyst with that?
ALCL free.
Right? Do you all agree?
Yes.
Okay, what will be the product?
Propane.
But let's not call it benzyl propane because that's totally different.
Yes.
What will it be?
Propylbenzene.
Propylbenzene. Okay, let's write a mechanism for that reaction. Step number one again is very similar. You'll see the similarities between this mechanism and halogenation. First step is the generating the electrophile. Till you have an electrophile, benzene cannot react and do anything with it. So the first step is, just like halogenation, the alkyl halide gives electrons to the Lewis acid. The Lewis acid wants electron density. That's why it's a Lewis acid. So just like halogenation, electron density is donated to the Lewis acid by the Lewis base. Just like halogenation, this creates an adduct. You guys remember adducts? Exactly the same. Now here there is a choice for this adduct. The choice for this adduct is A, that bond to break. And you tell me which one would it want to do. Okay, I'll show you both, but you tell me. One choice is option that, okay, if this breaks, that will neutralize the positive charge, right?
Mm-hmm.
But what will happen to the R?
R would become negative.
Are you sure?
No.
If it's giving electrons, how will it become negative?
Oh, it'll be a positive.
So what will propyl group become?
A carbocation.
What kind?
Primary.
Is that good?
No.
Why not? Primary carbocations are not stable. We never make primary carbocations unless they are resonance stabilized. Isn't that right? So do you think this would be a path this guy would
No.
want to take? No. Why? Because that's not stable. So for this system, that adduct cannot go beyond. It cannot go beyond it because it cannot make a stable carbocation. So for that system, once the adduct is created, benzene comes in and attacks like you would expect it to. The pi electrons, wrong direction. Wrong direction, sorry. The pi electrons attack there, which causes this bond to break and neutralize the positive charge without creating a primary carbocation. So a primary carbocation should not be invoked in any mechanism unless we can stabilize it by resonance. We good? What does this create? So what's the intermediate? What's the sigma complex look like? Yeah, and hydrogen.
Propane with a.
And
Oh, no,
this
never.
has the positive charge. And of course, right? So notice the similarity of the mechanism that we are writing with halogenation. The only difference is that instead of that second halogen, we have R. Otherwise, it's kind of the same thing. We good? So what do you think needs to happen next?
It has to give away a proton.
And who's gonna take a proton? Just like halogenation, you have an
Yeah.
extra Cl which can take electron density, takes the proton, recreates the aromaticity, making propylbenzene. Does that sound okay, everybody? Yes? Cool? Sure?
Yes.
Okay. So then, tell me, expected product?
Butyl benzene.
Third butyl benzene, tertiary butyl benzene, does everybody agree? Let's write a mechanism. So, what would be the first step? Just like halogenation?
The alkyl halide reacts with the Lewis acid to create an adduct.
Okay. So, and then
Okay. To write this first. And then
Benzene comes in.
but in this case, is that a good idea?
Oh.
Because that's a tertiary carbon, right?
mhm.
There's going to be steric hindrance for the benzene ring to come in.
True.
But can it do what this guy could not do?
No.
Yes.
Oh, I'm
Can
sorry.
this do what this guy could not do?
Yes.
Yes.
Why?
Because of hindrance.
Exactly. Because by doing so, it can create a stable carbocation. If the carbocation is stable, then yes, we will create it. If the carbocation is not stable, then we should not create. So in that case, yes, absolutely carbocation because it's stable. Then benzene will come in. The benzene in this case is going to attack the carbocation. Make sense, everybody? Yes? So if the benzene attacks the carbocation, makes a sigma complex, and then the sigma complex is going to lose a proton to create the products. So that loses a proton, this creates the pi bond again, everything becomes aromatic again. The point I'm trying to make here is, and that's why I wanted to show both of these side by side, is mechanism actually is kind of just like halogenation. The only difference is, in that stage, if the R cannot be a stable carbocation, then it will not be a carbocation, the benzene will attack the A duct and blah, blah, blah. But if R can be a stable carbocation, then we must make a carbocation, and then benzene comes in and attacks. Sounds okay, everybody? Yes? Okay, so let's try another one then. Once again, please keep in mind all of these different variations here. Okay, so please tell me what will be the product, and then we'll write the mechanism. Please tell me, what is the product? Anybody?
I don't know how to name it.
You do.
I mean, I
You
do,
know how to
but
make alkenes.
it'll take me a while.
How about 1-phenyl propene? No, sorry, 3-phenyl prop 1-ene.
Okay.
Okay,
Yeah.
okay,
Free
more like,
phenyl
okay, say so.
propionine.
We know how to name alkenes, guys. We learned those. Do you agree?
Okay.
Let's write a mechanism. So, what's the first step? The Lewis base attacks the Lewis acid, creates an ADA. Am I right?
Yep.
Now, next step here, this is where for alkylation reactions you have to pause because, oh, what are you doing, Sunita? Do you see the mistake I've made there? Can you catch my mistake?
You swap the charges.
Right? Something that gave electrons can't become negative, something that got electrons cannot become positive. Exactly, I swapped the charges. Agreed?
Yep.
Now here is where you have to pause and you have to decide, should this break the bond or should it not break the bond? Should it stay intact and benzene attacks here, or should this break and then the benzene attacks? Should it make a carbocation or not make a carbocation?
No.
Please, you got to pause. Don't be in a rush. You're saying yes? Why yes?
Because it's wait, no.
You're saying no, why no?
Oh.
I don't know. Is it alive? Why are you saying no, Carter?
Primary.
Okay?
But
Why
then
are you
it's
saying
also-
yes?
Because it's resonance.
Because it's not some simple primary, it's allylic
Primary
primary. So can it make a stable carbocation?
Yes.
Yes.
That is the key. If it can make a stable carbocation, then it must.
Hmm.
And allylic primary is extra stable. That's actually, I think it's just a little bit less stable than tertiary, but not too much less stable than that. So the point is, yes, absolutely. In this case, I definitely would expect this to create a carbocation. Do you agree?
Yes.
And then comes benzene. Attacks. Can I leave the rest for you guys? Right, because rest is the same. Benzene comes, attacks, makes a sigma complex, then loses a proton, creates the product. Are we all good? Everyone okay?
Mm-hmm.
Cool. Then I have, if that makes sense to you, then I have my next question for you. Excuse me. Product. Please think about it, not too long, but then decide, and you're basically running the mechanism in your head when you're thinking about it. You're basically kind of picturing the mechanism in your mind, right? And then deciding, oh, it goes this way or this way. So please, go ahead, tell me. Product. Major product. Anyone?
1, 2. Double free. 4. 1, 2, 3, 4. One phenyl, free methyl butene.
So why one phenyl? MNOP. Oh, sorry. Can you just cancel my question, Carter?
Okay.
You're absolutely right, because the other one will be 2,4, which is worse than 1,3. Absolutely. So what you're saying is this what you're saying, Carter? And everybody else, even though 1, 2, 3, 4, 1, 2, 3, 4. Is this what you're saying?
Yes.
How many of you are thinking this? What if I say that's not the major product? Let's process it. Let's write the mechanism and then decide, right? It's all about the mechanism. It's all about how is it happening, what is going on. So what's the first step? Anybody?
First step.
Lewis
The base attacks the acid.
Good. Creates the ADA, right?
Mm-hmm.
Okay. So if the Lewis base attacks the Lewis acid, creates the ADA, this is where there is a choice. And the choice is, if this bond were to break, will it create a stable carbocation or not? Isn't that right?
Yep.
Can this make a stable carbocation?
Yes.
Yes. Why is that stable? Because of
Resonance.
resonance. It's a Lilic primary. Okay. So do you agree? Isn't it?
Yes, but
Why? But
we have another one,
which is
the other side.
because of
Resonance.
resonance. Why aren't we thinking about, see there it was symmetrical. I raised it. The last example was symmetrical, it didn't make any difference. Now it does make a difference. What's the resonance structure? Isn't that right? Which is a more stable resonance structure?
Tertiary Lilic.
Do you guys agree? So the hybrid, and remember we keep saying this, resonance structures don't exist. What exists is the hybrid of the two. So what does the hybrid of the two look like? Well, the hybrid of the two definitely has electrons delocalized. Where are the positive charges?
Carbon 2 and carbon 3.
Do you guys agree? But here's the question, guys. If this is the more stable resonance structure, which resonance structure of the two, let's call it 1 and 2, will contribute more to the hybrid?
They're more stable.
Which is that?
The tertiary
Do you
Lilic.
agree? So the resonance hybrid resembles the more stable structure more. So, which carbon, 1 or 3, is more positive, more electron poor?
1 or free.
Because that's more stable. So if that's the case, where does the nucleophile want to attack in preference to the other side?
That one.
That one.
So which is the major product?
So then we just
Uh-huh.
move the diene.
It's not a diene.
I mean,
I know
diene.
what you're saying.
The
but
in. The in.
That's your major product. Because of the resonance. You're looking at both resonance structures, and the more stable resonance structure is the one that will give us the major product, because it's contributing more to the hybrid. Does that make sense, everybody? We good? Everybody got it? Sure? Rest of it you can complete it, right? Please make sure you complete the rest of the mechanism. Okay, so then here's another version of Friedel-Crafts alkylation. It's kind of the same thing, but yet a little different. Instead of an alkyl halide, no alkyl halide here. Instead of that, it's an alcohol. But with not a Lewis acid, but a Lowry-Bronsted strong acid. HF, by the way, hydrofluoric acid, is an extremely strong acid.
Which one's the strongest?
That's a good question. I know hydrofluoric might be even stronger than sulfuric. I think it is. It might be one of the, or maybe it's phosphorus something. I don't remember. Let's look it up. But it's, anyways, coming back though. This is not strictly exactly like that because there's no Lewis acid, there's no alkyl halide, but it does have things we know about. What happens when you have an alcohol with an acid? Come on, guys, you know this. What happens with an alcohol if you have an acid?
The alcohol becomes a good leaving group because it accepts it.
So the alcohol gets protonated, isn't that right?
Yes.
Have you seen that before?
Yes.
Yep.
Exactly, let's write it, okay?
I have an answer to that.
Say again?
I have an answer to this.
What is the answer to that question?
I'm gonna say it's HSB.
I have no idea what that is.
Okay. Fluoroantimonic acid.
Perfect, great.
HSBF6.
Whatever.
What?
Cool.
What was
Never-
that?
I've never actually seen that, I should go and look up its structure. So, sorry, what do you anticipate could happen between these two?
So take the drop.
Right? Exactly. Like we've seen
I-
hundreds of times before.
Mhm.
Right? Okay, what will that make? When that happens, what will that
A good
do?
living group.
The OH becomes a good leaving group, right?
Mm-hmm.
If it becomes a good leaving group, what does it do?
It'll
Leave,
disband from the.
right?
It'll
If it
disband
leaves, what will it
from the
make?
alkane.
In this
cat-
case,
A carbocation.
isn't that the same? As soon as you have the carbocation, what will happen?
The benzene.
Comes, attacks, sigma complex, blah, 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 blah. Can you please finish this mechanism? Because after this, everything is the same. So that's why I'm leaving it there. Are you guys comfortable with that? Everybody?
Very comfortable.
Cool. So that's, again, it doesn't have to, this is a variation, but again, look at the similarities. The logic is the same, that can we get something that's electron poor? Once you get something that's electron poor, benzene can attack it. We good? Here's another variation. Same logic, same idea, same thoughts. Okay, what about if it were this? Sorry, still on alcohol, but if it were this? And you're writing the mechanism and all. What would you do?
Will you get an alkoxide or?
Will you protonate the alcohol?
Yes,
Of course,
it's basically the
alcohol.
same
Oh,
as the hydrofluoric acid.
Yes, but there is a difference. What will you do next? Will you create a carbocation? Is the question. Why not, Jasmine? Exactly. Same rules. If unlike there where we had a tertiary carbocation, if I were to kick out water, that will be a primary carbocation. That's a no-no. Unless you can stabilize it with resonance, isn't that right?
Mm-hmm.
So this is where we don't make a carbocation. So what happens instead? Well, benzene comes in. Benzene comes in, attacks more like SN2 as opposed to SN1 kind of thing, and does the rest. The point I'm trying to make is, do not make a primary carbocation in any mechanism because primary carbocations are not stable.
Do they even exist?
If they do, very fleetingly. So not really something we should consider. Are we okay, everyone? Please, again, finish the rest. I'm just getting to the electrophile stage because after that, everything is the same. Okay, so here's another, instead of an alkyl halides or an alcohol, what if we had this written down somewhere? There we go. Oh, you know what? Let's use something else, which you might see as well. What is TSOH?
Tosyl alcohol.
Actually acid, toxic acid.
Toxic acid.
Again, TS structure you guys already know. Instead of the Cl at the end or the R at the end, we are putting an OH. It's an acid, but it's a very strong acid. It's not as strong as HF, but extremely strong acid because its conjugate base is resonance stabilized really well. So the point is, it's an acid, a strong acid. Everyone okay? So what do we expect to happen here? Anybody? Have you seen an alkene reacting with an acid before?
Yes.
Yes.
Good. What does it do when an alkene reacts with an acid?
The alkene takes the
Takes
The
the
proton.
proton. Good. And what does it become if the pi electrons take the proton? What does this become?
cation.
Carbocation.
Carbocation.
Carbocation. Again, all about carbocations. What kind of a carbocation? In this example, there are two possible carbocations, right? Either positive being here or positive being there. Isn't that right?
Correct.
Which one would you go with?
Secondary.
Exactly. Have we seen this before? Yes, hundreds of times. But,
Can we
go ahead.
rearrange?
There you go. If there is a carbocation in any mechanism, rearrangement is always possible. The rule is the rearranged carbocation more stable than the original or not? That's right here. So can this rearrange?
Yes.
What kind of rearrangement?
A methyl shift.
And if it does a methyl shift, what kind of a carbocation will it become?
Tertiary.
Yes, absolutely. And then benzene comes in and does its spiel, whatever it is. So what's the major product? Major product, what would that be?
Oh,
From that one,
from
right?
that one.
Good, so what does that look like? Once benzene comes and attacks the electrophile and makes a sigma complex and blah, 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 the major product comes from the more stable. Is that okay, everybody? Are you all seeing the patterns here? Okay, so now there are two limitations with Friedel-Crafts alkylation. That's why in lab actually we don't do Friedel-Crafts unless we can kind of sort of manipulate the process so it works in our favor. Most of the times we don't do Friedel-Crafts alkylation because there are two drawbacks, limitations to the Friedel-Crafts alkylation. One drawback or limitation of Friedel-Crafts alkylation
Is it TVT?
Okay, so the first one, please tell me. Let me draw it, then I'll ask you, okay? In all of these reactions, when you think of the mechanism, what is the role of benzene?
Stabilizing or
The
resonant?
That's not the
No.
question.
No.
What is benzene reacting as in all of
Oh.
these reactions?
The
Nucleophile.
nucleophile.
Is a nucleophile electron rich or electron poor?
Electron rich.
Okay, so when I'm doing Friedel-Crafts alkylation, this is acting as a nucleophile which is supposed to be electron rich, isn't that right?
Mm-hmm.
And I put an R group on it, whatever the R is. Great? Now, do you remember whether R is an electron donating group or electron withdrawing group? Does R give electron density or does R take electron density?
It takes electron density.
Guys, pause. Think about this. Think about this. Think about this. It's take or give, 50%, 50%. How do you come up with that conclusion? What made you decide that it gives, not takes? Okay?
I thought it gives to that.
If it's-
I was just
But
thinking
why?
like, like back to Gen Chem when we would do like,
Oh, you guys did this in Gen Chem?
no, I was thinking more like when we do like finding the polarity as like a source.
Oh,
Never
how,
spoke electron density.
Well, if that is rich.
but that's a carbon-carbon bond,
Oh,
isn't that?
Yes.
Isn't that a carbon-carbon bond?
Yeah.
Polarity probably is not gonna help you.
I was just thinking of the structure,
Okay.
like what it tended to do, to not take.
R. R meaning as an organic portion.
Oh my gosh, I see what you're saying. I was thinking carbon.
Oh, okay. So,
It's,
yeah, go ahead.
yeah.
What are you saying? Go ahead, Mark.
I was thinking it was also electron rich.
Good. Not electron rich. I'm not talking about electron rich or electron poor. I'm saying, is it going to give electron density to something that it's attached to, or is it going to take electron density from something it's attached to? Is it electron donating or is it electron taking? Electron accepting, electron withdrawing. Okay,
Electron taking?
How about giving?
so carbocations, let's go back to last quarter because we did talk about this last quarter. Carbocations, unsubstituted carbocation, primary carbocation, which is more stable of the two? Of these two, which is more stable?
The primary. Wait.
Is that what everybody said?
The one
Wait.
with the R?
Okay, is the first more stable or the second more stable?
Second.
Are we good?
More R. More,
So, why?
more organic.
As a bigger supply of electrons.
No, not bigger supply of electrons at all. But it's because the R group through the sigma bond by something called hyperconjugative effect. We didn't go into the details of hyperconjugative effect, by the way. We didn't, and you don't need to. But you do need to remember this, that R is an electron donating group. It doesn't take electron density. There's nothing electronegative or electron pulling about it, but it is able to, through something called hyperconjugative effect, is able to push some of this sigma bond electron density towards the other thing, whatever the other thing happens to be. That is why this positive is more stable than that positive. With me? Which is more stable, primary or secondary?
Secondary.
Why?
It's more R group.
It has
More
more
R
R's.
groups.
More of them are pushing some of this electron density towards the positive, stabilizing the positive. And that is why the tertiary is even more stable than secondary because it has 3 R groups. Point that I'm trying to make. R is an electron donating group, although weak, very weak electron donating, but electron donating nevertheless. We good? Everybody okay? Let me ask again. Is R electron donating or withdrawing?
Electron donating.
Donating.
So if it's pushing those electrons towards benzene, is the benzene more or less or same electron rich as before? Has the electron density of benzene gone up, gone down, or stayed the same as before? Do you all agree?
Yes.
Yes? This has become electron richer than before. We good? If it has become electron richer than before, who is the stronger nucleophile?
The R group, the benzene with the R group on it.
Than before. You've increased its nucleophilicity because it's electron richer. So, if one molecule reacts with whatever makes one molecule of that, and there is options of more molecules around, which of these two will attack the electrophile faster?
The
Stronger
R,
one.
the R benzene.
Which means it leads to
Polyalkylation.
Polyalkylation.
because every time you put an R on the ring, it becomes a nucleophilic, more nucleophilic, goes and reacts again. It becomes even more nucleophilic, goes and reacts again. And it just goes on and on and on. So that is a limitation, because why would we want more R's on it if I just want one? Can't control it. So that is, polyalkylation is a limitation of Friedel-Crafts alkylation reaction. Does everybody understand why?
Mm-hmm.
Every R makes the benzene even more electron rich than before, so therefore more nucleophilic than before, so therefore reacts with electrophile again and again and again. Everybody okay with that? Yes. Cool. Next limitation that exists for, excuse me, Friedel-Crafts alkylation, unless that's exactly what we wanted. And sometimes that's exactly what we want, so then it's great. But you tell me, please. What will be the major product? Here's the reaction, think about it, and tell me what will be the major product.
Wouldn't it be 1-methyl 1,3-diphenyl butane? Oh wait,
You're saying, so the expected product maybe was this. But that's not going to be the major product. You all agree? What will be the major product? Can you say that again, Carter? What?
methyl 1,3-diphenyl? Yeah.
1-methyl. Why 1-methyl?
Oh, 2,3-diphenyl
Why
butane?
2,3? Well, that's 2,3. Okay, so this is 2,3, right? Is that what you're thinking?
Yeah.
But that's not going to be the major product. That's expected because obviously that you're thinking about benzene attaching there. But that's not going to be the major product. Any guesses why? Yes.
It would be 1,1-phenyl, 1-methyl.
1,1-phenyl?
Diphenyl.
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 1,1-diphenyl.
1-methyl.
1-methyl.
Wait.
1-methyl, are you sure?
No. I take that back.
Let's try it again. Anybody?
1,1 diphenyl.
Not 1,1. 2,2. 2,2-dimethyl butane.
Yeah.
Why? That's going to be the major product. So without writing the mechanism, I'm not writing the whole thing, but do you guys agree that the Lewis base is going to attack the Lewis acid, make the adduct? Can this guy make a carbocation?
Tertiary benzoic?
Well, originally, what would it be? So once you get the adduct, can it break this bond and make a carbocation? Would you expect it to?
Yes.
Secondary? That's secondary.
Secondary.
We make those, right? But can this undergo rearrangement?
Yes.
And that's the problem. Absolutely it can, because then it's giving you a tertiary benzylic carbocation, which is probably the most stable possible. So, will this give us the major product, or will the rearranged one give us the major product?
The rearranged
Exactly,
one.
and that's also can be a limitation, because what if that's, I don't want rearrangement. If I don't want rearrangement, then that's a problem. If I want rearrangement, then yay. But if I don't want it, that's a problem. So that can be a problem, a limitation of this reaction, that carbocations can rearrange. There is one other limitation of this reaction. If you have benzene that is already connected to strongly electron withdrawing groups. So if you have a benzene, let's say for example, it already has a strongly electron withdrawing group, strong. And I'll tell you which ones those are in a second. Then Friedel-Crafts alkylation does not work. Doesn't work with benzenes that have lost most of their electron density because that group has pulled it all out of benzene, then benzene can't do anything. And strong electron withdrawing groups, we are talking about nitro is a very strong electron withdrawing group, trifluoromethyl is a very strong electron withdrawing group, and sulfonic acid is a very strong electron withdrawing group. So basically, if benzene already has one of those three groups on it, then cannot do Friedel-Crafts reaction, alkylation reaction, doesn't go.
So not carboxylic acid?
That does not fall under strong, that falls under a little bit less strong. And I'll give you, I'm not there yet, I think either later today or Monday we'll get to a point where I'll give you a list of groups in the order of their electronic characteristics. So that's not as strong an electron withdrawing as these three. These three are the strongest electron withdrawing groups that are out there. So then Friedel-Crafts alkylation just doesn't work. It doesn't help. So that can also be a problem in case that's something we want to do. Does not go with strong electron withdrawing groups, and those are the three that you probably want to consider. So, is there, okay, what do we do if we are stuck with one of these situations and we want to have the reaction? Well, then we first do Friedel-Crafts acylation. So let's look at this and we'll come back to that. So if we're stuck with these, what's a better way of doing Friedel-Crafts alkylation? Actually, a better way of doing alkylation is to do acylation first, and then working with the product. So Friedel-Crafts acylation, that's last of the 4 or 5 reactions. Acylation means we are putting an acyl group on the benzene. An acyl group is this group. This group is called acyl group. How do we do that? Well, very similar to Friedel-Crafts alkylation. Instead of an alkyl halide, we will take acyl halide with a Lewis acid catalyst. Same thing. X can be Cl, then the Lewis acid catalyst is AlCl3. X can be Br, then the Lewis acid catalyst is FeBr3. Exactly the same. Mechanism is also kind of similar, as we will see. So let's start with an example and then we write a mechanism. So if we are reacting benzene with, can someone tell me what will be the product? Although we can't name this product, so I guess we're not there yet.
So benzene.
So what will be the acyl group? Agreed?
Mm-hmm.
Everybody okay? It's this portion that goes. Okay, let's write a mechanism. So very, very similar to Friedel-Crafts alkylation and halogenation. First step, Lewis base attacks the Lewis acid, creates the adduct. Now, this is where somewhat there is difference, which in alkylation we have to gauge, will this bond break or not, because will the carbon be stable or not. Here we don't have to worry, because yes, it will break. Why? Because it creates something that is actually quite stable. What will it create when that bond breaks? Do you agree?
Mm-hmm.
Yes?
Yes.
Yes.
This is called, and maybe you can guess what that is called, because we organic chemists are not very creative with our naming. Guesses? No,
Which one's called, sorry?
Which one?
Acyl cation.
but it's a, how do we indicate that it's a cation?
Acyl anion?
Well, it's not an anion. Did you just say it's a cation? Let's call it, let's tell the reader it's an anion so they will know it's a cation. What's the ending all cations have? Think about, and this is not organic, this is in general.
Oh, yeah.
Exactly. This is acylium.
Acylium.
Is a cation. Ammonium, hydronium, nitronium. The
Acylium.
ium is anion. I mean, I just you just
Cation.
messed with my brain. Ium is a cation. Ide is always an anion. Always.
I'd.
Okay. Anyways, acylium ion is actually quite stable. Why? How?
Resonance.
Exactly. From where?
The C double bond O.
Meaning, which part of CW? Do you think those electrons will go here? Not really. Those electrons can't go here. Anybody?
It can go to the next CC bond.
Really? That's sp3.
Oh no, it can't.
sp3 to the oxygen. What about oxygen?
Oh,
Are electrons going to oxygen? Are we doing, when you said to oxygen, is this what you're suggesting?
Yeah.
Let's think about this. What will that do to the carbon here? It's already positive. Does it want to become more positive? No. If the carbon is positive, if this carbon is positive, does it want to give electrons or get electrons?
get electrons.
Can't give. If I'm already poor, you can't take money from me because I don't have it. Make sense? But if I'm poor, you can give me money because that's the direction it flows. Make sense, right? Same thing. So the point is, this carbon is positive, it wants electrons. Who's going to give it electrons? Can it be this carbon?
No,
So what is the option?
the oxygen.
The lone pairs on the oxygen. If the lone pairs on the oxygen come, do they go directly to the carbon? No, they go to the bond. They make what? What does that become?
A triple.
Exactly, a triple bond. And where's the charge?
Plus on the oxygen.
And now I'm going to ask you a question which you've got to think about and use what we learned in 261. Which resonance structure, first one or second one, is more stable?
Second one, because they all have octets.
Exactly. And it's sometimes difficult to see, but you gave a positive to, factor comes later. Whenever you are assessing the relative stabilities of resonance structures, the first thing we look at octets. Which structure has most number of octets? And that is this structure. That one, carbon, does not have an octet. It has only 6 electrons, not 8. This one has all atoms fulfilling octet role. So please just don't go by, oh, but that's oxygen, more electrons. That doesn't matter. Actually, that doesn't matter. So yes, that's a very stable intermediate because it is resonance stabilized, acylium ion. And that is your electrophile. Once that is created, benzene can come in, and just like before, again, it doesn't matter which resonance structure you use for your mechanism, because remember, hybrids exist, resonance structures don't exist. That's totally up to you. Once the acylium ion is created, benzene, I lost track. Oh, benzene attacks the electrophile, creates the sigma complex. Sigma complex loses a proton because we have that guy over there, sigma complex. Gives us the product. So the electrophile in Friedel-Crafts acylation reactions is this acylium ion, which is resonance stabilized. Once again, guys, I chose to write this resonance structure. You could have written it with that resonance structure. Totally okay. That's totally fine.
But should we show both of them in our?
This is the more stable resonance structure. So most books you follow will use that because it's the more stable one.
So when you're writing your sigma complex, you don't necessarily have to write them all three.
No, you don't have to. No, you don't. Everybody okay? So that is the mechanism for Friedel-Crafts acylation reaction. So if that makes sense, why don't you guys write it one more time so that, by the way, can there be rearrangement? Is there any danger of rearrangement in that example? In this reaction, I should say. Are we making any carbocation that could rearrange?
No.
No, exactly. There's no carbocation that can rearrange or so on and so forth. So, okay, why don't you guys go ahead, tell me what will be the product. Oh, what? Why do I have that? So I wasn't thinking. Please tell me what will be the product. Here's another one. Okay, does anybody have product for this one? And no, we don't know how to name that.
See,
It's okay.
So benzene and then
Uh-huh.
line and then
Alkyne, did you say?
CO
Oh, okay, yeah. And
and
the
then the third
T-butyl. You all agree? Everybody okay? Agreed? Basically, it's this portion, the acyl part, which attaches to the benzene. Are you all okay to write the mechanism for that? Everyone good with that?
Well, it's like that.
Exactly. There's going to be no difference. Cool. How about this one?
Now you got it.
So the point is, can this reaction happen intramolecularly? Do write the mechanisms, guys. Again, as you heard me say this plenty of times, the more times you write a mechanism, the better you will remember it. So do write all the mechanisms to make sure you're getting that muscle memory. But can this reaction happen intramolecularly?
Yes.
If so, what would be the product? Now, one thing to keep in mind in terms of intramolecular reactions, most of the time, especially here, it will happen if it can make a 5 or a 6 membered ring. Because whenever you do something intramolecular, you're going to make a ring, right? Because if this arm attaches to this arm, you're going to make a ring. So in these reactions, can it happen intramolecular? Absolutely. But if by doing so, the new ring is either a 5-membered ring or a 6-membered ring. Otherwise, no. Make sense? Okay, so can it do intramolecular? And what will it be? What would the product be? Name it. No, I'm just saying. No, we can't. You want to draw it for me? No. Anybody else? Yeah, please. It's okay.
She's thinking about it.
Ooh, are you breaking benzene ring? Okay, so where is that going? Which carbon is that going to? And I think that's where you're going, that's the exact direction you're going, absolutely. Please, can we draw it?
I think I just got tripped up and said 600.
The new ring, if it can be a 5 or a 6-membered ring, then intramolecular reactions are more probable. Please write all mechanisms. When you're studying, you should be writing. I strongly believe there is a greater retention when you are seeing, writing, and speaking. The retention is higher. Please do. Do you all agree? Everybody agrees? Did everybody get that kind of sort of thing? So that gives us the product. Again, write a mechanism. Make sure you got it. How? Why? What's going on? How? Please do.
I don't exactly know how that happens.
Okay, write a mechanism, try it out. Let me know once you've written a mechanism what you get. So we said, actually, why don't we use that as an example for the where we're supposed to go? So this is the Friedel-Crafts. How many was it?
5.
1, 2, 3. Okay, so this step is Friedel-Crafts acylation reaction, isn't that right?
Mm-hmm.
Now we said Friedel-Crafts acylation reaction is a way to overcome the limitations of Friedel-Crafts alkylation reaction. How so? Because when you get the acylation product, this can be converted into alkylation product by reducing the double bond. There are 3 possible ways of doing so. We can reduce the C double bond O in the acylation product to CH2. C double bond O becomes a CH2 using 3 different reactions. One is a simple hydrogenation technique. Mostly platinum, but that's one of the ways to do it. Although that's a bit slow. That reaction is a bit slow. So most of the times we don't do it, but it is okay. I mean, sure, it's slow. The more common ways of converting the acylation product into alkyl benzene is to do what is called Clemmensen reduction, which is zinc amalgam. What is an amalgam? Amalgam is basically a metal that's fused with mercury. So it's like an alloy. So zinc amalgam, meaning zinc is fused with mercury, but under acidic conditions. This is called Clemmensen's reduction. This happens under acidic conditions, as you can see. The other common way is called Wolff-Kishner reduction, which happens under basic conditions. It uses hydrazine. Hydrazine is NH4 used with a base. This is called Wolff-Kishner reduction. Now please, let's pause, because hydrazine, N2H4, this guy is called hydrazine. Can someone tell me what is its Lewis structure? N2H4, what does it look like?
And single bond N.
Mm-hmm.
And then each nitrogen has 2 H's on it.
And what What else? What's missing?
Oh, a lone pair
Which is where?
on each end.
So sometimes, instead of writing N2H4, they could show you the structure. We should recognize it's the same thing. Sometimes they may write it as this. It's the same thing. So that's why I want us to, the structure matters. We got to know what does this look like. Oh, that's what it is. So hydrazine with base KOH is called Wolff-Kishner reduction. Zinc amalgam with HCl is called Clemmensen reduction. And this is under obviously neutral conditions, not acid nor base, but it is relatively a slow process. So not as common, but why not? Okay, so let's try this. You know, I don't want to draw benzene like 5 times. It's the same benzene. Let me just draw it once. Do we need this on the board or can I erase this board?
You can erase it.
Clemenson's is only for acylation or also?
No, all
Also-
of these are for reducing the acylated product to alkylated.
Acylated to alkylate?
Yeah, they're
Oh,
reducing, their
Okay.
reduction, C double bond O gets reduced to CH2,
okay.
right? All 3 of them. 3 ways of doing that. Okay. While you're doing that, and feel free to come to the board and write the answers. Okay, we'll get to that.
1, 2,
That's
3.
summarizing everything we've done so
1,
far in this
2,
chapter before we go to the next step.
3.
But do we have answers here?
And then finally the N2H4 KOH.
Anybody?
Sorry, broken?
Answers?
Oh.
Oh, and there's the other one.
Right there.
One, which is the lacial.
Do you have extra carbon for the, not you, Camilla, do you have?
This one?
Yeah.
You can
Am I counting wrong or? No, I think you do have extra. Do you agree with the React stuff on there? What about the missing ones?
Oh, the Grignards?
Why not? Yeah. You want to write that, Carla? about the last one? Yeah, you didn't have space, yeah. Do you go home, Vivian, and have like this grip in your neck? Because you have that, feel free to move where you can actually, don't have to twist and turn so much. Okay, good.
One, two, three, double.
Ooh, think about the double bond though.
Double bonds at the end, so 1, 2, 3.
How about the last one, guys? Anybody?
This one?
Yeah.
I'm still working through it, but I think.
Job remembering the Grignard, Carter.
Thanks.
Especially because we did this in the lab. I'm just going to make it bigger.
Okay.
Lost a carbon. See, count your carbons. 2 are coming from benzene, right?
Yeah.
And then how many are coming from the other guy? Total of 4. So that's 6. Do you see what I'm trying to say?
Yeah.
Absolutely. Could you, before you go, Hila, could you draw the product from step 1? Okay, and then what does that become before it becomes the final product? So what are we getting at the end of step 1?
Oh, I see what you're saying.
Right? Because
Yeah.
step 1 is going to actually happen twice because there are 2 ACL groups. And yeah, exactly. First one will do Fieldcraft acylation, but then there is one other one ready to cyclize and make that, which then gets reduced to perfect. Do you all agree? Any question on anything? Now guys, one thing I would suggest is the more times you write mechanisms, the better you will remember. So please do. Just, that's part of the practice thing, that you watching some movie and just writing mechanisms. Yeah, okay, so let's summarize what we've done so far, because so far we've learned 5 reactions with their mechanisms. Let's summarize those. So benzene can react with chlorine with the Lewis acid catalyst, and what will be the outcome? Agreed?
Yep.
It will react with bromine with the Lewis acid catalyst to produce, right? What is produced when benzene reacts with fuming sulfuric acid? Anybody?
As benzene sulfonic acid.
Good. And then benzene sulfonic acid can be hydrolyzed back to benzene by using dilute sulfuric acid. So it's a reversible process. Depending on what you use, you can go in one or the other direction. Can someone tell me, what do we get when we react benzene with nitric acid and sulfuric acid?
A nitrobenzene.
Nitrobenzene, and nitrobenzene can be reduced using this reaction to
Anisole.
not anisole.
A
You mean aniline.
aniline.
That's exactly what
Anisole is
That's
methoxy.
OCH3, yeah.
Yeah. Aniline. Agreed? Friedel-Crafts alkylation, if we do that, I mean, we should know the mechanisms and all of that stuff, even though there are limitations with it, you're really bound to come across those. That produces alkylbenzene. Friedel-Crafts acylation produces acylbenzene. And what we've also said is that acylbenzene can be converted into alkylbenzene 3 different ways. One is Clemmensen reduction, the other is, which is zinc H mercury with HCl, the other is Wolff-Kishner using hydrazine with potassium hydroxide and simple hydrogenation, also with hydrogen with a heavy metal catalyst like platinum or palladium or nickel, can also be converted into that. That's what we've done so far. Any questions? Mechanisms that you should be able to write? Absolutely, absolutely, yes, 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 yes. Those are the mechanisms we should know. Questions? Okay, sorry. So far, by the way, all of this stuff that I'm doing, as I told you the other day, I have these notes all on Canvas, FYI. All these notes right here is on Canvas. Anyways, coming back though. So far, we have looked at only benzene doing one of these 5 possible reactions. But what about if we are doing these reactions on substituted benzene? Meaning benzenes that already have a group or 2 on them, and then we are trying to do one of those 5 reactions, then how will the things go? The mechanisms are the same, but then what would the outcomes be? So that's our next discussion. So electrophilic aromatic substitution on substituted benzenes. By the way, electrophilic aromatic substitution, what is being substituted?
The
Electrophile is substituting what? Hydrogen. And that's something you have to pay attention to, that, oh, when electrophilic aromatic substitution happens, the electrophile is replacing a hydrogen on the benzene. That's the important part. So the idea here is that if we have a substituted benzene, by the way, this is a format which you might see written. What does that even mean? This is a very general way for us to say that the group, whatever it is, can be anywhere there, okay, because we don't know where it is. Actually, maybe I would write it differently. Okay, let me write it differently. But yeah, that's a format you might come across. So please, the only thing that means is this thing can be anywhere on those carbons, any of those carbons. Okay, so let's say there's already a group on the benzene. Let's start with 1, and we are doing an electrophilic aromatic substitution reaction. How many possible products, can possibly be created? 3. What would they be?
The ortho, para, and meta.
Exactly. The point is, if there is one group on the benzene, now there are 3 possible places that the electrophile can go to. It can either go to one of the orthos, or one of the metas, or one of the paras. Or the para, there's only one para, right? So the possible products are 3 regioisomers, the ortho substituted, the para substituted, or the meta. Exactly. Do we all remember ortho, para, meta, right?
Yes.
Okay, cool. So there are 3 possible products based upon what is being what G is. It all depends upon what is this, because then that decides the outcome. So let's focus on the G. The G can either be an electron withdrawing group, a group that pulls electron density away from the ring towards itself, or it can be an electron donating group, a group that pushes electron density into the benzene ring. It gives electron density to the benzene ring. Do we all understand these terms? Everybody? Yes? Okay, cool. So, and I'll give you a handout with a list and blah, 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 but before we go there, if let's say, excuse me, if let's say the group that is already on the benzene is an electron withdrawing group, it is pulling electron density towards itself from the benzene, right? Is that making the benzene ring more electron rich, less electron rich, or no change?
Less electron rich.
Everybody agrees? So, what will that do to the nucleophilicity of the benzene?
It'll decrease it.
Exactly. So, therefore, electron withdrawing groups, they make the benzene ring less electron rich, which basically means less nucleophilic than benzene itself. Isn't that right? Everybody okay? Yeah? So then, if that's the case, if G is electron withdrawing, will this reaction go faster or slower or no change?
Slower.
Everybody agrees? Isn't that right? The whole job of benzene is to be electron rich. So if you're taking the electron richness away, it's going to react slowly. Hence, these groups are called deactivating groups because they are making the benzene ring less active towards electrophilic aromatic substitution. Does that make sense, everybody? The comparison, the point of comparison is benzene with nothing on it. That's a point of comparison. So what do you expect to happen if, on the other hand, the benzene ring were attached to an electron donating group? An electron donating group pushes moves electron density to the benzene. So do you expect this to make the benzene more electron rich, less electron rich? No change.
More electron rich.
And if it is more electron, benzene becomes more electron rich, will it react faster or slower with an electron?
Faster.
Exactly. Which means it's a
More.
better nucleophile or increases its nucleophilicity. So what's the opposite of deactivating?
Activating.
The point I'm trying to make here is, if the group that is already on benzene is an electron withdrawing group, it deactivates the benzene towards the electrophile. The reaction goes slower. But if the group is an electron donating group, it activates the ring to react with the electrophile. The reaction goes faster. Make sense, everybody? Yes? Okay. So, I did my... Here. Could you please pass these? Sorry. Pass these. Just make sure it just goes around. I'm not counting or anything.
Thank you.
Here you go.
Okay. By the way, I think this table is on Canvas somewhere as well if you need. I have, did everybody get? Wow, why do I have so many? Okay, thank you. Okay, so what I'm giving to you is a list of groups. How would you know whether a group is deactivating or activating, meaning electron withdrawing or electron donating? So there are some commonalities that you might come across, that you might see when it comes to us recognizing them. One of the things you will see with the electron withdrawing groups is that the atom, whatever that is, it doesn't have to be carbon, by the way, it can be nitrogen, it can be something else, but whatever the atom is, can I just say A for atom?
Yep.
Whatever that is, has a pi bond, doesn't have to be with oxygen, but has a pi bond to an atom B, whatever that is. Because, and this atom is more electronegative. So if that is more electronegative, because of resonance, electron density gets sucked out towards B. B acts as a sink, it starts pulling electron density towards itself. That's one of the common things you will see. So for example, if you see the list, do you see how this is an electron withdrawing group? Atom with a pi bond to an electronegative atom. Benzene is attached here. This is the place where benzene is. Agreed? So anytime you have a C double bond O attached to the benzene, whether it's an aldehyde or a ketone or an ester or an acid, carboxylic acid, or whatever the case might be, those are electron withdrawing groups. There's another one that you might see in that list, which is nitrile. Do you see that?
Yep.
Same thing, a pi bond to a more electronegative atom so that it can pull electron density towards itself. Then the most electronegative, excuse me, I said that wrong. The most electron withdrawing groups of all, as we mentioned those before, are nitros. Again, if you look at the structure of nitro, same thing. Same thing. There's another one, sulfonic acid, same thing. Structurally, that's the commonality that makes these groups electron withdrawing. The benzene is attached to an atom that is pi bonded to a more electronegative atom, so that guy sucks electron density out due to resonance. There is one electron withdrawing group that does not have resonance but is strong electron withdrawing group, and that is CF3. That's just because fluorine is insanely electronegative. That's why in most of our discussions we don't talk about fluorine, because its electronegativity is way high. But these are the three very strong electron withdrawers. Right? Everybody okay? As far as donating is concerned, they will fall under two categories. They will either, there's also halogens that are very weakly electron withdrawing because electronegativity mostly. But it's all on that table. Electron donating will fall under two categories. One is the stronger electron donators will be the ones that have benzene attached to an atom, whatever that atom is, which can have whatever bonds, but it has lone pairs. That atom that benzene is connected to has lone pairs. Because if it has lone pairs of electrons, those lone pairs of electrons can be pushed into the ring through resonance, making the ring more electron rich, which these guys don't have. That atom does not have lone pairs, can't have lone pairs. Because if it has lone pairs, then it falls in this category. So for example, you see OH is a very strong electron donating, very strong electron donating. These are the the strongest electron donators are those two. Strongest electron donators are OH and NH2. And the others that you see in order, of course, OR, same thing, you see that? Or you see an ester, but not from the CO double bond O side, but from the single bonded O side. Same thing. NH, same, amines, same thing. Same thing. You'll see that commonality in all of them. And the other category, which we saw a bit ago, is just alkyl. Those are weak electron donors because it's not resonance. It's kind of sort of like what do you call it? inductive effect, but not resonance. So weak effect, but yet electron donors. So the handout that I've given you arranges all these groups in order of their electron donating versus electron withdrawing capacities. Don't focus on the orientation part yet. That column, we haven't gotten to that yet. We'll do that on Monday. Focus only on the middle column, or rather, effect on rate, reactivity part. So activating groups are the ones that give electrons to the benzene. Deactivating groups are the ones that take electrons from the benzene. These are the activators, these are the deactivators. Make sense, everybody? Yes? Okay, so,
Quiz
shoot, we are
on
not ready
Monday.
for this. Okay, I guess we'll have to stop here.
Quiz on Monday and
Yes, quiz
lab
on
on Tuesday.
Monday. Quiz on Monday will cover everything we've done till this part. So please, even though we haven't had a chance to look at some specific examples, but now knowing that electron donating groups make the ring more reactive, electron withdrawing groups make the benzene ring less reactive, we can answer some questions on that. So the plan for Monday after the quiz, we will cover the regioselectivity part and do some more I think I can finish this chapter on Monday. At least that's my thought. Okay? Cool. Have a great one, everybody.
Yeah, thank you.
Yeah, thank you, Samita. You're welcome.
We're gonna have office hour tomorrow, right?